Okay, everybody, welcome to another wonderful session of physics here. We're going to do some practice problems. This is our unbalanced forces unit, and the main thing here that we are doing a little bit differently is we are taking away the fact that all of the forces are equal, left to right, up to down. In one of those directions, one of those key directions, you are going to have unbalanced forces, where you're going to have items that are not equal any longer, and that's kind of our new change. So in order to get off to a strong start, what I was hoping to do is do a little bit of review on some of these practice problems that we started in class today, or, well, a day or two ago. Alrighty, so here we go. Um, this first one, by the way, is I want to say around page 78-ish, somewhere in your textbook. All right, this is practice number 1. And this first problem, it has been a long while since we have seen a problem with an inclined plane. So let's do some quick review about how the inclined plane free body diagram works. First, we're going to have gravity. Right, Fg is on its way down. We have a normal force which is perpendicular to the surface because we are on a surface. In this particular question, if you look at the prompt, it tells you that you're moving with a constant speed. So I know for certain I'm going to need to have friction, and friction will be going up the inclined plane. And the reason I know that is because when I go to do the next piece of this, where I actually break my gravity apart into its components, that this piece, by the way, that's the same angle, that's the same 20 degrees, right? This piece, the sine piece, right? This is my opposite side here, this is my hypotenuse over there. That is going to try to go down the hill, always. Gravity never tries to pull anything up a hill, so they're going to go down the hill. This one then needs to have friction going back up the hill, or it can't move with a constant speed. All right, so that's a quick review right there of what is going on. Now, let's take a look at this particular problem. This particular problem says what models apply to the situation and why. Now, if you're kind of wondering what the heck does that question even mean, well, we've had 4 models that we've studied. Constant velocity, meaning things are moving with a constant velocity. Constant acceleration, which means they're not moving with a constant velocity. They're actually getting faster or slower. The PM, in case you're wondering, stands for particle model. Okay, so that is why it's CVPM, CAPM. Last but not least, what causes our constant velocity? Balanced forces. So the balanced force particle model, and then this new one that we're working with, an unbalanced force particle model. So according to our question, we are moving with constant speed. So that tells me right away constant velocity. And what has to go with constant velocity is balanced forces. That's the reason we have constant velocity. If we have constant acceleration, the reason we have constant acceleration is because the forces are not balanced. Then it says to draw at least 4 diagrams or graphs. Now we've just done one over here with this free body diagram, so let's consider some other ones. Not all of them are as useful as the others, right? A position time graph, if we are moving with a constant speed, is going to look like this. And it's fine, it looks great, but honestly, the money graph, the one that really helps us out, is velocity time. And this is the one that is going to be moving with a let's see if I don't really have a whole lot of space on the left, so I'll write it over here. 1.4 meters per second on the right. That is our constant velocity graph. We've got a nice flat line there because we aren't getting any faster or slower. All right, acceleration time. This is one that really didn't get pulled up too much in class, but we don't have an acceleration, right? The slope of that line is going to tell me the acceleration, and it's 0. So, okay, that should really, this is the smart board being funny. All right, but that should be 0. No acceleration. Now, I'm telling you right now, this is the graph that will help you out the most mathematically. That's the one you want. So between those, it's fine. The other one that some folks brought up was a motion map. If you're going to do a motion map with velocity, just remember that your arrows should be approximately the same size because you're moving with a constant velocity. Okay, so now what I've asked you to do is to solve for absolutely everything you can possibly find. Right, and we've done some of the work here in terms of figuring out what our free body diagram is going to look like. Now in the question we have a 80-kilogram object. All right, let's put some of this stuff over here. All right, so we've got 80 kilograms, that's our mass. So that means that m times g, which is going to be my force of gravity, I should have that here someplace. Well, heavens to Betsy, lo and behold, I don't. It's going to be somewhere around 800, so what is it, maybe 768? I'm trying to remember from the last question, because I did not bring my calculator over here. I just brought my answer key, which is so naughty. Okay, so, nope, I still didn't do it. I still don't have it. I'm going to guess it's around 768, but you can correct me if I'm wrong. All right, so then we can figure out our mg sine theta. That's going to be important. This may or may not work with, since again, I'm just going to be going off of my answer key here for numbers. Make sure you're in degrees, not radians when you do this one. So 268. The mg cosine theta is this piece. That's my adjacent side with my hypotenuse. Mg cosine of theta. Theta is 20 degrees, by the way, in case you're wondering what I mean by theta. That's going to be 737 newtons. Okay, why is this important? Well, let's consider when we do balanced forces, right? What balanced forces tells us is that up equals down, left equals right. Let's consider what we've got then. Okay, up equals down. I'm going to consider that this direction of motion here. That's my up equals down. So that means my mg cosine theta going down has to match my normal force going up. So that tells me, I think my adjustment is off a little bit here, huh? 737 newtons for that one. All right, my up equals down. I'm talking about up and down the hill. Up and down the hill. So friction is trying to go up the hill. Mg sine theta is trying to go down the hill. And so both of those will be equal to 700. Nope, I looked at the wrong one. 268 newtons. Alrighty, what else can I figure out? Well, if you figure I know friction and I know normal force, it's not too much of a stretch to figure out coefficient of friction, because that's the friction force divided by the normal force. When I do that, I'm going to get 0.364, which would be my coefficient of friction. Again, I haven't been told I have to figure this out, but I'm just trying to figure out absolutely everything I can do. Okay, last but not least, let's take a look at our velocity time graph. I'll switch colors here to make it a little easier to see. All right, but again, well, actually, you know what? I don't need to do that, do I? Because I have a perfectly fine velocity time graph right up here. All right, I've even labeled it, if you can read that, 1.4 meters per second for my velocity. And it goes down to 2 meters. Now remember, 2 meters, that is my area under the curve. All right, and this is my y coordinate. This tells me how far I'm going from here to here. So the last thing I can figure out is the time it will take for the object to actually, make it down. So I'm going to do that work over here. Just in case you're wondering, I have the most room, of course, right? So if I want to know how far I'm going, this is a rectangle. I'm going to do the length times the width. So 2 meters equals 1.4 meters per second. Time final. My time final, 1.43 seconds. All right, so that is pretty much everything I can figure out about that first question. And so I'm ready to move on. And for whatever reason, when we had these printed, there was a mix-up, and we, all right, let's go. There we go. I was hitting it with my finger, waiting for it to switch the page, and it wouldn't do it. I guess I need to use the marker. All right, but for whatever reason, the Elevator Lab got stuck in there. So let's go back to this one. And again, darned it, you know what? I'm going to take just a minute here. Oh, Mr. Marsh left me a calculator. That is awesome. So let's just do a little quick gravity. Yep, 784. Okay, so same free body diagram. We've got mg. We've got normal force. We've got friction. friction with an F. That's what I'm looking for there. And then I'm going to put in my components, right? mg sine of theta. Again, remember that's my opposite side, right? My hypotenuse is always mg cosine of theta. Now, the reason, if you're wondering again, why do we have to do this to the gravity? It's because of the way this box is going to accelerate. Right now, it's saying it's opposed by a friction force that's 150 newtons. So we're being given that value, right? If you have something on a hill, chances are it is going to accelerate down the hill. So what we do is we make the Cartesian plane in the direction of the acceleration, right? So that it matches. This is the whole tilting thing we always talk about. When you look at it that way and you consider a tilted Cartesian plane, the only thing that's a diagonal is mg, which is why we're making a triangle out of it. You only make triangles out of the things that are diagonals. You don't need to make a million triangles just because we love triangles. All right, and it can get a little confusing with the ramp, but gravity is it. This is all we're going to do. Okay, so according to this trusty little tiny calculator over here, because you know Mr. Marsh teaches earth science, so he doesn't need the fancy calculators that we have. It's actually 785 newtons for mg. My mg sine theta is still going to be 268 newtons. That hasn't changed. My mg cosine theta, I'm sorry how sloppy this is, right? It's still going to be 737 newtons. But let's consider what that means, right? So this is 268 newtons. That sure as heck does not match 150 newtons. It really doesn't. That means we have an acceleration because our forces are not balanced. They are not equal. But they're not unbalanced everywhere. We're not going totally crazy, right? The 737 newtons here is still 737 newtons here for my normal force. This block is not levitating or sinking through the ramp. So these two must be equal. Alrighty. Now, let's consider, we've already figured out quite a bit here for certain, but let's take this to the next level. If we have forces that are unbalanced, we are going to use Newton's second law to figure out the acceleration. Newton's second law is ma, but then there's that fancy Grady equation I keep talking about because, you know, why not, right? This is going to be the bigger force minus the smaller force. All right, so let's consider the mass is 80. I'm looking for A. My bigger force is actually trying to go down the hill. It's the mg sine theta. My smaller force is the friction force trying to go up the hill. So when I do the math here, right, I'm going to get 80A, and let's see, 268 minus 150, so that's what, 8 and 118 newtons divided by 80, and I get an acceleration of 1.5 meters per second squared. That's pretty easy. That's actually doesn't have 1,000 decimals to it. That's kind of crazy. All right, but anyway, that is the acceleration of my object going down the hill. So now let's consider, we can still figure out how long it's going to take that object to get to the bottom of the hill. So again, what's my best graph? My velocity time graph. I am looking at an object that is beginning from rest and it is headed down the hill. And while it is being opposed by friction force, which is fine, I know the slope of the line is still 1.5 meters per second squared. I also know the length of the ramp is still 2 meters. So I've got that going for me. All right. When I have these graphs, I'm going to use two different equations. I'm going to use the area under the curve, which is going to involve TF VF, right? That's the area of a triangle right there. TF is going to be over here. VF is going to be up here. All right, the other thing I'm going to work with, now if I get rid of the 1/2, that's what I have. I can't get any further, but I can work with the slope of the line, which is 1.5. 1.5 equals, actually let's change the color so that it looks a little easier to see. All right, so we'll put that there. Final velocity minus the initial velocity of 0. Final time minus the initial time of 0. So obviously these drop out, right? If I cross multiply, I get rid of the TF on the bottom. I get this value I'm going to put it right there. Okay, so 4 equals 1.5 TF squared. Divide by 1.5 and then take a square root and you'll have this one. Okay, so 2.7 is TF squared, TF 1.63 seconds. That is everything we can figure out about this particular one. Okay, that's everything. Between those two, you should be able to do inclined planes. At least I hope so. My goodness, I seriously hope so. All right, that free body diagram is really critical. So that is something that we absolutely want to do. All right, this one we did in class. So I'm skipping a little bit ahead and I'm going to take a look at this guy over here. You guys did a great job of free body diagrams here. All right, we've got mg trying to go downward. You still have friction, or I'm sorry, normal force. Your tension force is here, and you know that it's 400 newtons because the question tells you so. All right, this is a 30-degree angle. And then, yeah, we're going to have some friction. We don't have a lot, it turns out, but we do have some. So you need to take care of that. Now, let's consider this diagonal of 400 newtons. It's really easy to figure that, wait, let's start making triangles out of gravity because that's what we did in the last problem. But you don't need to do that. You only do that for things that you have a triangle for. Okay, I would consider this to be a tension force because, you know, the guy's pulling on a rope. So if I consider that's Bx and that would be y, I'm going to simply work with the vectors, the arrows that I have there. Okay, now I've gotten lots of questions about how to draw those arrows. Take a look at the black arrow. It's up and to the left, which means your two legs of your triangle need to be up and to the left. That's why I drew them that way. Okay, I'm not going down. I'm not going to the right. Don't draw sticks. Draw arrows. You know why? Because the fact that this arrow points up is really important for our math in a few minutes. Okay, so you know, take care of business that way. All right, I'm going to go back to black here. Let's figure a few of these out. mg is easy. We always can start there. All right, so we're going to do 70 kilograms times 9.81 for that one, and we're going to get 687 newtons. After that, you can figure out Tx and Ty. Tx is the cosine component, cosine of 30 times 400. And when you do that, you get 346 newtons. Ty is going to be the sine component because it's the opposite side. And that's going to give me 200 newtons. So I now know the value of both of those. So if this one is 200 newtons, right, and this one is 687 newtons, that gives you the opportunity to figure out the normal force. It's not 687 newtons up here. That's everybody's first guess. But you have two arrows pointing up, this one and this one. So you have to add them together to add up to the 687. So normal force has got to be 487 newtons. Sorry if that's hard to read, but that's the best I can do on this board. I'm running out of space. The next big thing that everybody wants to do is say that the friction equals 346. But no, it doesn't, because this box starts from rest and travels like that. That's not a box with constant velocity. That's a box that's accelerating. Okay, so a VT graph would be handy here. It's going to look like that again. Okay, VT graph, it travels 15 meters in 2.47 seconds. All right, so we cannot set friction equal. You just can't. It doesn't work. You want to because it's easier, but that would make an acceleration of 0, and the slope of that line is clearly not 0. So let's figure it out, shall we? That would be a good one. Let's start out by figuring out the final velocity here at the end. Okay, for that I'm going to use, well, I'm only got 2 to choose from, right? So whichever one first, right? Let's do base times height. That's our triangle. All right, so 15 meters equals 1/2. The base is 2.47 seconds, and I'm solving for VF. 30 equals 2.47 VF. I multiply both sides by 2. VF, I don't know what happened there with the pen. Sorry, guys. This part doesn't have, the red pen really doesn't seem to be lined up. All right, so there's my VF. It's 12.15. Now I have the ability to find the slope of the line. Slope of the line is going to be 12.15 meters per second minus 0. And my TF is 2.47 minus 0. And so that makes my acceleration to be 4.92 meters per second squared. And this is a really critical piece of information. Let me tell you why. Acceleration obviously is part of our VT graph, but it's also part of forces. When you have unbalanced forces, acceleration is the common link between the motion and the forces. So we need this. We need this. And if you consider what we know about the horizontal motion, we know that net force has got to be equal to the bigger force minus the smaller force. Again, Grady's equation, right? MA equals, well, which one's my bigger force? TX, the guy's pulling on the rope, it's going to slide to the left. The smaller force is going to be the force of friction. So let's consider 70A equals 346 newtons minus force of friction. Oh, wait, 70A, I'm so silly. I know what A is. What am I doing? All right, so 70, that's kilograms, by the way, times 4.92 meters per second squared. All right, so realistically, I'm only missing the one thing. I'm only missing the friction. So when you do the work, right, this is going to be about 344 newtons, and you're going to, and you might say, wait a minute, I'm going to end up with negative. No, you're not. Hang on. Friction's negative over here, so let's move it to the left. Right, and then let's move over. All right, 344 over here. Right? Make sense, I hope? All right, so my friction in the end turns out to be 1.6 newtons. It's kind of tiny. If I go to figure out my coefficient of friction from that, which, as a reminder, friction over normal. What this tells me is 1.6 newtons and whatever I figured out for my normal force, 487? I think it is 487 newtons. So my friction turns out to be, or my mu is pretty small. There's my last piece. I figured out everything. 28 steps later. So you know what, guys? If this is making sense, good for you. This is not easy stuff. I mean, I know that I make it look so easy, or that we act like, maybe it should be easy. It's not easy. This is good. This is really complicated stuff. You should be proud of yourself if you've got a decent understanding of this. And if you don't, you need to do some more practice. That's all. That's why we're doing this here today, right? So we can do a little more practice. Come on now. Let's switch the page. Come on, next page. All right, look, I left myself extra room just in case. Let's try it again. Come on, next page. Oh, there's our last one. I think I left myself an extra page on this one too, just in case. But I think we're going to be all right. This is actually quite similar to the last one, with the exception of my direction of this arrow. Now it is going down, so my normal force is going to change, right? Look at the way my arrows go. If I'm pushing down on something, I am going down and to the left. That means that my leg arrow's got to be down and to the left. That's how we do that. All right, we know that one. We know that one. Okay, so let's, what did I do here? Oh, I called it something different in my answer key. No big deal. All right, mg is down here. Normal force, still going up. And well, I usually wouldn't write it on the left side, but let's keep it out of the way of the other triangle, shall we? All right, so we've got this box being pushed. The box is starting from rest and again traveling 15 meters in 2.8 seconds. So we are going to have, let's start with a VT graph over here. It's getting faster. All right, so we definitely want that. 15 meters, 2.78 seconds. Gosh, are these the same numbers as before? I thought it was, but maybe it's not. 2.47, 2.78. Ugh, of course not. So we have to do extra. We have to do extra, but it shouldn't be that hard, right? We want to get to the acceleration there. That's going to be the piece that we need. Okay, so let's start with area under the curve. It's a triangle, so I'm going to use 1/2 base height. 15 equals 1/2 times 2 point, let's write it down correctly, Grady, 78. And the height is what I'm looking for. That's my final velocity here. All right, so that'll be final velocity. 30 equals 2.78 VF, because I moved the 2 over. VF is going to be equal to 10.8 meters per second. Then I'm going to do the acceleration, which is going to be the slope of the line. My final velocity is 10.8. My initial velocity was 0. 2.78 minus my initial time of 0. So my acceleration then turns out to be 3.88 meters per second squared. Hopefully we are all good with that. This is going to be the critical piece that I need for the free body diagram over there. Okay. Man, that is loud. Hang on. Nope. These are not lined up properly, so I wasn't able to hit the pause button. I apologize. All right, but again, this one's going to be 70 kilograms, 9.81 meters per second squared on that one. So we're going to have 687 newtons over here. You want to make the normal force 687. I know you do, but it's not. Okay, let's figure out this well, I suppose technically it's not a tension, but so that we don't have like two confusing normal forces, let's just call it a tension, shall we? All right, so 400 newtons times the cosine of 30 is going to be the TX, because it's my adjacent side. 400 times the sine of 30 is going to be TY, because that's my opposite side. So I know TY is 200, because I know that the sine of 30 is 1/2. So that one's going to be 200, and then my 346 for this one, just like last time. Okay, but again, friction is not going to be the same as the TX. We want it to be, but this is unbalanced. This is accelerating. I do not get to just say, oh yeah, let's make these equal. What you say instead is net force equals mass times acceleration. It also equals the bigger force minus the smaller force. And you ask yourself, where are they not balanced? Oh, whoops, you know what I just realized? I didn't figure out the normal force. Let's figure that out first, okay? So 687 is my gravity. 200 newtons is also going down. You notice I have 2 arrows going down. So that means that my normal force, which is the only up arrow, is the 2 of those combined. All right, so let's not forget normal force. We would need that if we're doing the coefficient of friction anyhow. All right, so mass is 70 kilograms. My acceleration, I figured out from over here, is 3.88. The bigger force is going to be TX, because this box is still sliding to the left. So 346 newtons minus the force of friction. Okie dokie, let's figure out the old force of friction, shall we? 271 newtons over here. 346 minus the force of friction. Now again, move over the force of friction. It should be positive force of friction plus 271 equals 346. Then subtract away the 271. You know, if you're confident, do it in your head, but otherwise write it down. I mean, having that step written down gives you just a little more confidence that you're doing it right. All right, just like math class. 75 newtons for your friction force. Kabam. Last thing we could possibly figure out is coefficient of friction. Again, that is friction force divided by the normal force. And friction is 75. Our normal force is 887. Therefore, 0.085 is our final answer. Okay, I hope that these practice problems kind of get you an idea of where we are going. We are going to be toggling between motion and forces for a while now because now we have all of these tools. We've been putting small pieces of the puzzle together. We're actually putting the entire puzzle together now about how knowing the forces on an object and the mass of that object allow us to predict where that object is going to go. So kind of a big deal. I hope this clarifies things for you. Please, 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 please come find me if you have questions. All right, enough with that bell. I'm going to sign off. Talk to you soon.